Question 1. What factors determine the most appropriate high-availability strategy for a critical Linux-based service, considering the need for minimal downtime and efficient resource utilization within a regulated environment? Option A. The selection of the most technologically advanced and feature-rich high-availability solution available, regardless of complexity or immediate cost. Option B. A comprehensive assessment of the service's criticality, acceptable downtime tolerance, existing infrastructure capabilities, scalability requirements, and the total cost of ownership, including implementation, maintenance, and potential recovery expenses. Option C. The lowest initial acquisition cost for high-availability software and hardware, prioritizing immediate budget constraints. Option D. A solution that relies on proprietary technologies with limited community support, assuming it offers superior performance metrics. Correct answer is B. A comprehensive assessment of the service's criticality, acceptable downtime tolerance, existing infrastructure capabilities, scalability requirements, and the total cost of ownership, including implementation, maintenance, and potential recovery expenses. Explanation. This scenario presents a professional challenge in balancing the immediate need for system availability with the long-term implications of a chosen high-availability solution. The senior Linux administrator must consider not only technical feasibility, but also the operational costs, maintainability, and adherence to organizational policies, which are implicitly governed by the regulatory framework relevant to the LPI Level 3 Exam 304. The core of the challenge lies in selecting a high-availability strategy that is robust, cost-effective, and aligns with the organization's risk tolerance and compliance requirements without compromising service integrity. The correct approach represents best professional practice because it prioritizes a comprehensive evaluation of all relevant factors, including technical requirements, operational impact, and financial considerations, before committing to a specific high-availability solution. This aligns with the principles of responsible IT management, which are often underpinned by regulatory guidelines that mandate due diligence, risk assessment, and cost-benefit analysis in technology deployments. Specifically, a thorough assessment ensures that the chosen solution is not only technically sound, but also sustainable and compliant with any applicable service-level agreements or internal governance frameworks. An incorrect approach that focuses solely on the lowest initial cost fails to consider the total cost of ownership, including potential downtime costs, maintenance expenses, and the cost of future scalability. This can lead to a technically inadequate solution that is more expensive in the long run and may violate implicit regulatory requirements for service continuity and operational efficiency. Another incorrect approach that prioritizes a bleeding-edge technology without sufficient testing or proven stability risks, introducing unforeseen issues, potentially leading to service disruptions. This can be seen as a failure in risk management, which is a critical component of many regulatory frameworks governing IT infrastructure. A third incorrect approach that ignores the expertise of the existing IT team and opts for an overly complex solution that requires specialized, unavailable skills can lead to poor implementation and ongoing maintenance challenges, potentially violating guidelines related to operational competence and resource management. The professional decision-making process for similar situations should involve a structured approach. First, clearly define the business requirements and acceptable downtime windows. Second, identify potential high-availability solutions that meet these requirements. Third, conduct a thorough technical and financial evaluation of each viable option, considering factors such as complexity, scalability, vendor support, and total cost of ownership. Fourth, assess the risks associated with each solution, including potential failure points and mitigation strategies. Finally, document the decision-making process and the rationale for the chosen solution, ensuring it aligns with organizational policies and any relevant regulatory obligations. Question 2. When evaluating potential high-availability solutions for a critical virtualized Linux environment, which approach best balances rapid failover capabilities with system stability and data integrity? Option A. Choose the most cost-effective high-availability solution available, potentially by reducing redundancy in network components or storage, to minimize initial capital expenditure, with the understanding that some level of downtime is acceptable. Option B. Select a vendor-provided, out-of-the-box high-availability solution and deploy it with default settings, relying on the vendor's assurance of reliability without extensive environment-specific testing. Option C. Implement a solution that prioritizes the absolute shortest recovery time objective, RTO, by aggressively configuring automatic failover mechanisms, assuming that any downtime is more costly than potential data inconsistencies during a transition. Option D. Design and implement a high-availability solution based on a thorough understanding of application dependencies and failure tolerances, incorporating staged testing of failover scenarios, continuous monitoring, and a well-defined rollback plan. Correct answer is C. Implement a solution that prioritizes the absolute shortest recovery time, objective RTO, by aggressively configuring automatic failover mechanisms, assuming that any downtime is more costly than potential data inconsistencies during a transition. Explanation. This scenario presents a professional challenge in ensuring the integrity and performance of a critical virtualized infrastructure, specifically concerning high availability. The core difficulty lies in balancing the need for rapid recovery from failures with the potential for introducing instability or data corruption through aggressive, untested failover mechanisms. Professionals must make informed decisions that align with established best practices and the implicit requirements of maintaining service continuity, which are paramount in senior-level Linux and virtualization roles. The correct approach represents best professional practice because it prioritizes a systematic, data-driven, and risk-managed strategy for implementing and testing high-availability solutions. This involves understanding the specific application workloads, their tolerance for downtime, and the underlying hardware and network capabilities. Thorough testing, staged rollouts, and continuous monitoring are essential to validate the effectiveness of the HA solution and to identify potential issues before they impact production services. This aligns with the professional responsibility to deliver reliable and robust systems, minimizing service disruption and data loss. An incorrect approach that focuses solely on minimizing recovery time without adequate testing or understanding of the application's behavior during failover is professionally unacceptable. This could lead to data corruption, application instability, or even complete system failure during a real outage, directly contradicting the goal of high availability. Such an approach demonstrates a failure to conduct proper due diligence and risk assessment, potentially violating implicit service level agreements and professional standards of care. Another incorrect approach that relies on default or vendor-provided HA configurations without customization or validation is also problematic. While defaults can be a starting point, they may not be optimized for the specific environment or workload. Failing to tailor and test these configurations can result in suboptimal performance, unexpected behavior, or security vulnerabilities, all of which are detrimental to professional system administration. This oversight can lead to a false sense of security and expose the organization to unnecessary risks. A further incorrect approach that prioritizes cost savings over robust HA implementation, perhaps by choosing less reliable hardware or skipping essential redundancy components, is a significant professional failing. High availability is often a business requirement driven by the cost of downtime. Compromising on the fundamental elements of HA to save money directly undermines the purpose of implementing such solutions and can lead to far greater financial losses in the event of an incident. The professional decision-making process for similar situations should involve a structured approach. 1. Understand requirements. Clearly define the business needs for high availability, including acceptable downtime windows and recovery time objectives, RTO, and recovery point objectives, RPO. 2. Assess environment. Analyze the existing infrastructure, including hardware, network, operating systems, and application dependencies. 3. Evaluate solutions. Research and compare different HA technologies and methodologies suitable for the Linux environment and virtualization platform. 4. Risk assessment. Identify potential failure points and the impact of each, and evaluate the risks associated with different HA strategies. 5. Design and plan. Develop a detailed design for the HA solution, including failover procedures, testing plans, and rollback strategies. 6. Implement and test. Deploy the HA solution in a controlled environment. Conduct rigorous testing to simulate various failure scenarios and validate performance. 7. Monitor and maintain. Continuously monitor the HA system, perform regular health checks, and update configurations as needed. 8. Document. Maintain comprehensive documentation of the HA design, implementation, and operational procedures. Question 3. The control framework reveals a critical service failure within a virtualized, high-availability Linux cluster. The primary node has become unresponsive, impacting service availability. The system administrators are tasked with restoring service as quickly and reliably as possible, adhering to the operational and security guidelines expected for a senior-level Linux certification. They must choose the most appropriate immediate action to mitigate the outage. Option A. Manually reconfigure the service on a separate, non-clustered server, bypassing the existing high-availability setup to expedite restoration. Option B. Attempt to restore the service from the most recent available system snapshot without first verifying its integrity or its compatibility with the cluster's current state. Option C. Immediately begin a complete rebuild of the affected server from scratch, disregarding existing cluster configurations and backup data. Option D. Initiate the automated failover process to the secondary node within the existing high-availability cluster, ensuring the process is logged and subsequently verified against established recovery point objectives. Correct answer is D. Initiate the automated failover process to the secondary node within the existing high-availability cluster, ensuring the process is logged and subsequently verified against established recovery point objectives. Explanation. Scenario analysis. This scenario presents a common challenge in high-availability environments, balancing the need for rapid recovery with the imperative of data integrity and compliance. The core tension lies between minimizing downtime, a key objective of high availability, and ensuring that any recovery process adheres strictly to established security protocols and audit trails, as mandated by the LPI Level 3 Exam 304 syllabus. The professional challenge is to select a recovery strategy that is both effective and compliant, avoiding shortcuts that could compromise security or lead to regulatory violations. Correct approach analysis. The correct approach prioritizes a documented, tested, and compliant recovery process. This involves utilizing the pre-configured high-availability cluster's failover mechanisms, which are designed to automatically or semi-automatically transition services to a standby node. Crucially, this process must be integrated with the organization's established backup and restore procedures, ensuring that any data loss is within acceptable recovery point objectives, RPO, and that the restored state is consistent and verifiable. Adherence to the LPI Level 3 Exam 304 principles means leveraging the virtualization and high availability features in a manner that maintains system integrity and allows for post-incident auditing. This approach represents best professional practice because it directly addresses the high availability requirement while embedding security and compliance checks throughout the recovery lifecycle, aligning with the robust operational standards expected at a senior Linux certification level. Incorrect approach is analysis. Manually reconfiguring services on a separate server without leveraging the existing HA cluster or established recovery procedures is a significant regulatory and ethical failure. This bypasses the tested failover mechanisms, introduces a high risk of misconfiguration, and creates an unmonitored, undocumented recovery path. Such an approach violates the principles of controlled system management and auditability, which are fundamental to maintaining system integrity and compliance. Attempting to restore from a recent snapshot without verifying its integrity or ensuring it aligns with the cluster state can lead to data corruption or inconsistencies. This is a failure to adhere to best practices for data recovery and can result in a non-functional or compromised system, directly contravening the goals of high availability and potentially violating data integrity regulations. Performing a full system rebuild from scratch without utilizing the HA cluster's capabilities or a validated backup is inefficient and introduces unnecessary downtime. While it might eventually restore functionality, it ignores the purpose of investing in high-availability solutions and the established recovery protocols, demonstrating a lack of understanding of the exam's core competencies. This approach also risks introducing new vulnerabilities during the manual rebuild process. Professional reasoning. Professionals facing such a situation should first consult their organization's documented disaster recovery and business continuity plans. These plans, informed by the principles covered in the LPI Level 3 Exam 304, should outline the approved procedures for handling service disruption. The decision-making process should involve assessing the nature and scope of the failure, identifying the most appropriate recovery mechanism within the HA framework, and ensuring that all actions are logged and auditable. Prioritizing tested, documented, and compliant recovery methods over ad hoc solutions is paramount to maintaining system stability, data integrity, and regulatory adherence. Question 4. Stakeholder feedback indicates that users are experiencing intermittent performance degradation during live migration operations within the virtualized production environment. The current setup utilizes a highly available storage array with its own internal redundancy mechanisms, and the virtualization hosts are configured for high availability. The administrator suspects a potential conflict or bottleneck between the live migration process and the storage array's high availability features, which could be causing the observed slowdowns. Which of the following approaches is the most professionally sound and technically responsible method for diagnosing and resolving this issue? Option A. Immediately disable the high availability features on the storage array to eliminate it as a potential bottleneck, and then retest live migration performance. Option B. Apply a generic performance tuning script to the virtualization hosts, focusing on network and disk I/O parameters, to see if it resolves the migration performance issues. Option C. In a staging environment that mirrors the production setup, simulate live migrations while meticulously monitoring I/O performance metrics on both the source and destination hosts, as well as the storage array. Simultaneously, analyze the virtualization platform's logs for any specific errors or warnings related to storage access during these operations. Option D. Escalate the issue directly to the storage array vendor, providing them with the initial user feedback and requesting a full system diagnostic of their hardware. The correct answer is C. In a staging environment that mirrors the production setup, simulate live migrations while meticulously monitoring I/O performance metrics on both the source and destination hosts, as well as the storage array. Simultaneously, analyze the virtualization platform's logs for any specific errors or warnings related to storage access during these operations. Explanation. This scenario presents a common challenge in high availability environments, balancing performance optimization with the inherent complexities and potential risks of advanced virtualization features. The professional challenge lies in understanding the subtle interactions between different high availability mechanisms and their impact on system stability and data integrity, especially when dealing with a critical production system. A senior Linux administrator must not only possess deep technical knowledge, but also the foresight to anticipate potential failure points and the ability to implement solutions that adhere to best practices and any relevant, though not explicitly stated in this exam context, implied by professional standards, operational guidelines for data protection and service continuity. The correct approach represents best professional practice because it prioritizes a controlled, phased implementation and thorough validation. By first isolating the issue to the specific high availability feature, e.g., live migration, and then testing its interaction with the storage layer in a non-production environment, the administrator minimizes the risk of introducing instability into the live production cluster. This methodical approach, involving detailed logging and performance monitoring, allows for early detection of anomalies and provides concrete data for troubleshooting. It aligns with the principle of least privilege in change management, ensuring that any modifications are understood and verified before impacting critical services. An incorrect approach that involves immediately disabling the storage array's high availability features without a clear understanding of their role in the overall cluster's resilience would be professionally unacceptable. This action could inadvertently create a single point of failure at the storage level, directly contradicting the goal of high availability and potentially leading to data loss or extended downtime if the storage hardware were to fail. It demonstrates a lack of analytical depth and a reactive rather than proactive problem-solving methodology. Another incorrect approach, such as blindly applying a generic performance tuning script without understanding its specific impact on the virtualization and high availability stack, is also professionally unsound. Such scripts might inadvertently alter critical kernel parameters or I/O schedulers in a way that destabilizes the cluster, particularly affecting the delicate balance required for live migration or failover operations. This approach bypasses the necessary diagnostic steps and risks introducing new, unforeseen problems. Finally, an approach that involves immediately escalating the issue to the storage vendor without performing any initial local diagnostics would be inefficient and potentially costly. While vendor support is crucial, a senior administrator is expected to perform initial troubleshooting to gather relevant data and narrow down the potential causes. This demonstrates a failure to leverage internal expertise and could lead to unnecessary delays and miscommunication. The professional decision-making process for similar situations should involve a structured approach. 1. Clearly define the observed problem and its impact. 2. Gather all relevant system logs and performance metrics from the affected components, virtualization host, guest OS, storage. 3. Formulate hypotheses about the root cause, considering the interaction of different technologies. 4. Prioritize testing of hypotheses in a controlled, non-production environment. 5. Implement changes incrementally with clear rollback plans. 6. Thoroughly validate the effectiveness and stability of any implemented solution. 7. Document all findings, actions, and outcomes. Question 5. Process analysis reveals that a critical virtualized infrastructure supporting multiple high-availability services requires a significant upgrade to its hypervisor and storage backend. The primary concern is to minimize any potential disruption to these services during the upgrade process. Which of the following approaches best addresses this concern while adhering to best practices for virtualization and high availability? Option A. Execute the upgrade during the organization's busiest operational period to ensure maximum user impact is observed immediately, allowing for rapid identification of any problems. Option B. Implement the upgrade directly on the production cluster during a scheduled maintenance window, relying on the inherent high availability features of the existing cluster to mitigate any issues. Option C. Conduct a comprehensive impact assessment and develop a phased rollout plan, including extensive testing in a staging environment that mirrors production, followed by an incremental deployment with a well-defined rollback strategy. Option D. Prioritize the upgrade of the most critical service first, performing the full upgrade on that service's virtual machines, and then proceeding with the rest of the cluster. The correct answer is C. Conduct a comprehensive impact assessment and develop a phased rollout plan, including extensive testing in a staging environment that mirrors production, followed by an incremental deployment with a well-defined rollback strategy. Explanation. Scenario analysis. This scenario presents a common challenge in virtualization environments, ensuring the integrity and availability of critical services during a planned infrastructure upgrade. Professional challenge lies in balancing the need for modernization and performance improvement with the absolute requirement of uninterrupted service delivery, especially in a regulated environment where downtime can have significant financial and compliance repercussions. The complexity arises from the interconnectedness of virtualized systems, the potential for cascading failures, and the need to meticulously plan and execute changes without impacting live operations. Correct approach analysis. The correct approach involves a phased, risk-mitigated rollout strategy that prioritizes minimal disruption. This aligns with best professional practices for change management in IT infrastructure, particularly in virtualized and high-availability contexts. By performing a comprehensive impact assessment that includes thorough testing in a staging environment mirroring production, followed by a controlled, incremental deployment with robust rollback procedures, the risk of service interruption is significantly minimized. This methodical approach ensures that potential issues are identified and resolved before they affect live users, thereby upholding service-level agreements, SLAs, and maintaining operational continuity. This is crucial for demonstrating due diligence and adherence to operational standards expected in senior-level IT roles. Incorrect approach is analysis. Implementing the upgrade directly on the production cluster without prior staging or a phased rollout is a direct violation of sound IT change management principles. This approach introduces an unacceptably high risk of widespread service disruption, potentially leading to data loss, significant financial penalties due to SLA breaches, and reputational damage. It demonstrates a failure to conduct a proper impact assessment and a disregard for the principles of high availability. Performing the upgrade during a peak operational period, even with a rollback plan, is professionally irresponsible. Peak hours are when the demand on services is highest, making any disruption more impactful and harder to recover from quickly. This approach prioritizes speed over safety and demonstrates a lack of understanding of operational impact and user experience. Focusing solely on the technical implementation of the upgrade without considering the broader operational and business impact, such as user experience, data integrity, and compliance requirements, is a critical oversight. This narrow focus neglects the holistic responsibilities of a senior IT professional and can lead to unforeseen consequences that undermine the overall success of the project and the stability of the environment. Professional reasoning. Professionals facing such a scenario should adopt a structured decision-making process that begins with a clear understanding of the business objectives and the criticality of the services involved. This is followed by a detailed impact assessment, which includes identifying all dependencies, potential failure points, and the consequences of downtime. The next step is to design a deployment strategy that incorporates risk mitigation techniques, such as staging, phased rollouts, and comprehensive rollback plans. Communication with stakeholders, including end users and management, is paramount throughout the process. Finally, continuous monitoring and validation during and after the deployment are essential to ensure the stability and performance of the upgraded environment. Question 6. Governance review demonstrates that the primary virtualized storage cluster supporting critical customer-facing applications has experienced a catastrophic failure. The disaster recovery plan mandates a maximum recovery point objective, RPO, of 15 minutes and a recovery time objective, RTO, of 2 hours. The backup strategy includes immutable snapshots of the primary storage, designed to prevent accidental or malicious alteration. During the incident, the team identifies that the most recent immutable snapshot is 10 minutes old, well within the RPO. However, restoring directly from this immutable snapshot would require a complex, multi-step process to re-establish the application's transactional consistency, potentially pushing the recovery time beyond the RTO. The team is under immense pressure to restore services immediately. Which of the following actions represents the most professionally responsible and compliant approach to restoring services? Option A. Halt all recovery efforts until a complete, in-depth investigation into the root cause of the storage cluster failure is concluded, to ensure no similar issues arise in the future. Option B. Restore from an older, non-immutable backup that can be brought online faster, accepting a higher RPO and potential data loss to meet the RTO. Option C. Initiate a restoration from the most recent immutable snapshot, meticulously following the documented multi-step process for transactional consistency, even if it risks exceeding the RTO, and immediately begin root cause analysis post-recovery. Option D. Bypass the immutability controls on the immutable snapshot to expedite the restoration process, prioritizing the RTO over data integrity and auditability. The correct answer is C. Initiate a restoration from the most recent immutable snapshot, meticulously following the documented multi-step process for transactional consistency, even if it risks exceeding the RTO, and immediately begin root cause analysis post-recovery. Explanation. Scenario analysis. This scenario presents a common challenge in high-availability environments, balancing the need for rapid disaster recovery with the imperative of data integrity and regulatory compliance. The pressure to restore services quickly after an incident can lead to shortcuts that compromise data accuracy or violate established protocols. The professional challenge lies in adhering to strict RPO/RTO objectives while ensuring that the recovery process itself does not introduce new risks or violate data governance policies, particularly concerning data immutability and audit trails. Correct approach analysis. The correct approach prioritizes a validated, tested, and documented recovery procedure that explicitly accounts for the immutability requirements of the sensitive data. This aligns with best practices for data protection and compliance. By leveraging a predefined, tested disaster recovery plan that includes specific steps for handling immutable backups, the organization ensures that data integrity is maintained even under duress. This approach demonstrates a commitment to robust governance, risk management, and adherence to regulatory frameworks that mandate data protection and auditability. It reflects a mature understanding of the interplay between operational resilience and data security. Incorrect approaches analysis. One incorrect approach involves bypassing the immutability controls on the backup data to expedite the restoration process. This is a significant regulatory and ethical failure. It directly contravenes data governance policies designed to prevent unauthorized modification or deletion of critical data, which is often a requirement for compliance with regulations like GDPR, HIPAA, or SOX, depending on the jurisdiction. Though for this exam, we focus on general principles applicable to senior Linux certifications. Such an action would destroy the audit trail, making it impossible to verify the integrity of the restored data and potentially leading to severe penalties, legal liabilities, and reputational damage. Another incorrect approach is to proceed with a restoration from a non-immutable backup source without proper validation or documentation. This introduces a high risk of data corruption or loss, as the integrity of the source cannot be guaranteed. It also bypasses established procedures, undermining the auditability of the recovery process and potentially violating internal controls and external regulatory requirements for data handling and disaster recovery. This approach prioritizes speed over reliability and compliance. A third incorrect approach is to delay the recovery significantly to conduct an exhaustive, ad hoc investigation into the root cause of the failure before initiating any restoration. While root cause analysis is crucial, delaying recovery beyond acceptable RTOs without a clear, documented justification and communication plan is professionally unsound. It can lead to prolonged service disruption, financial losses, and customer dissatisfaction, and may also violate service-level agreements, SLAs, and regulatory obligations to maintain business continuity. The focus should be on a swift, compliant recovery, with root cause analysis conducted in parallel or immediately post-recovery. Professional reasoning. Professionals in this domain must adopt a risk-based decision-making framework. This involves 1. Understanding and prioritizing RPO/RTO objectives. 2. Thoroughly understanding the organization's data governance policies and relevant regulatory requirements, especially concerning data immutability and auditability. 3. Relying on predefined, tested disaster recovery plans. 4. Evaluating recovery options against both operational and compliance requirements. 5. Documenting all decisions and actions taken during the recovery process. 6. Communicating transparently with stakeholders about the recovery status and any deviations from standard procedures. In situations of urgency, the framework emphasizes adherence to established, compliant procedures over ad hoc, potentially risky shortcuts. Question 7. The efficiency study reveals that the virtual machine failover time in the high availability cluster has increased by 30% during simulated network interruptions, exceeding the acceptable threshold defined in the operational guidelines. The administrator suspects a misconfiguration in the cluster's fencing mechanism, which is designed to prevent data corruption during network partitions. Which of the following actions represents the most professional and effective approach to resolving this issue? Option A. Immediately disable the fencing mechanism to observe if failover times improve, and then re-enable it later if the issue is resolved by other means. Option B. Analyze the cluster logs and fencing device status for error messages or anomalies. Then systematically review the fencing configuration parameters against best practices and the specific requirements of the virtualization and HA software. Option C. Increase the network timeout values for the cluster nodes to allow more time for communication before initiating a failover. Option D. Revert the entire cluster configuration to a previous known good state without further investigation into the specific cause of the increased failover time. The correct answer is B. Analyze the cluster logs and fencing device status for error messages or anomalies, then systematically review the fencing configuration parameters against best practices and the specific requirements of the virtualization and HA software. Explanation. The efficiency study reveals a critical bottleneck in the high availability cluster's failover mechanism, specifically impacting the virtual machine's ability to seamlessly transition during simulated hardware failures. This scenario is professionally challenging because it directly affects the core promise of high availability, uninterrupted service. The senior Linux administrator must not only identify the root cause, but also implement a solution that adheres to the stringent requirements of the LPI Level 3 Exam 304, which emphasizes robust, reliable, and secure virtualization and high-availability configurations within a defined regulatory framework, assumed to be a generic, best practice framework for IT operations, as no specific jurisdiction is provided beyond the exam context. The correct approach involves a systematic, evidence-based troubleshooting methodology that prioritizes data integrity and minimizes service disruption. This means analyzing cluster logs, performance metrics, and configuration files to pinpoint the exact cause of the failover delay. Implementing a solution that has been thoroughly tested in a staging environment before deployment to production is paramount. This aligns with best professional practices for IT operations, ensuring that changes are validated and do not introduce new risks. Focus on understanding the underlying mechanisms of the virtualization and HA software, rather than superficial fixes, demonstrates a commitment to long-term system stability and compliance with the spirit of the LPI certification, which aims to validate senior-level expertise in these critical areas. An incorrect approach would be to hastily reconfigure network settings without a clear understanding of their impact on the cluster's quorum or fencing mechanisms. This could lead to split-brain scenarios or prevent the cluster from forming correctly, violating the principles of high availability and potentially causing data corruption. Another incorrect approach would be to disable certain HA features to speed up failover, as this directly contradicts the exam's focus on robust high availability and would likely introduce significant risks of downtime and data loss, failing to meet professional standards. A third incorrect approach might be to rely solely on vendor support without performing independent analysis, which, while a valid step, should not replace the administrator's own diagnostic efforts and understanding of the system's behavior. This demonstrates a lack of proactive problem-solving and a potential failure to fully grasp the system's intricacies, which is a hallmark of senior-level expertise. The professional decision-making process for similar situations should involve 1. Thoroughly understanding the problem statement and its impact. 2. Consulting relevant documentation and logs. 3. Formulating hypotheses and designing tests to validate them. 4. Prioritizing solutions based on risk, impact, and feasibility. 5. Implementing changes in a controlled manner with rollback plans. 6. Verifying the effectiveness of the solution and documenting the process. Question 8. Quality control measures reveal that a critical host within a high-availability Linux virtualization cluster requires immediate firmware updates to address a newly discovered security vulnerability. The cluster is configured with shared storage and multiple redundant network paths, supporting several mission-critical virtual machines. The goal is to apply these updates with the absolute minimum disruption to the running services. Which of the following approaches best satisfies the requirement for minimal disruption and adherence to high availability principles? Option A. Attempt to perform the firmware update on the host while the virtual machines are still running to save time. Option B. Schedule a complete system shutdown for all virtual machines and the host to perform the maintenance during a designated maintenance window. Option C. Initiate a live migration of all virtual machines from the target host to other available hosts within the cluster before proceeding with the firmware update on the isolated host. Option D. Immediately shut down the target host to prevent any potential issues during the firmware update process. The correct answer is C. Initiate a live migration of all virtual machines from the target host to other available hosts within the cluster before proceeding with the firmware update on the isolated host. Explanation: Scenario analysis. This scenario presents a common challenge in high-availability environments, ensuring data integrity and service continuity during planned maintenance. The professional challenge lies in balancing the need for system updates with the imperative to minimize downtime and data loss, all while adhering to strict operational procedures and potentially regulatory compliance requirements for data handling and system uptime. The complexity arises from the interconnectedness of virtualized systems and the potential for cascading failures if not managed meticulously. Correct approach analysis. The correct approach involves a phased, controlled migration of virtual machines to an alternate host within the cluster, followed by a graceful shutdown and update of the original host. This method represents best professional practice because it leverages the inherent capabilities of the virtualization platform for live migration, thereby minimizing or eliminating service interruption for the running applications. It ensures that data remains accessible and processing continues uninterrupted. This aligns with the principles of high availability and disaster recovery, which are core tenets of senior-level Linux administration and virtualization. From a regulatory perspective, minimizing unplanned downtime and ensuring data integrity are often implicit or explicit requirements for business continuity and data protection. Incorrect approaches analysis. One incorrect approach is to immediately shut down the host without migrating the virtual machines. This would result in immediate service disruption and potential data loss for any unsaved transactions or processes running on those VMs. This is a direct violation of high availability principles and would likely breach service level agreements, SLAs, leading to significant operational and reputational damage. Ethically, it demonstrates a lack of foresight and a disregard for the impact on end users and the business. Another incorrect approach is to attempt to perform the updates on a live, running host without any form of migration or failover. This is highly risky and could lead to system instability, crashes, and data corruption during the update process. It ignores the fundamental principles of safe system administration and virtualization management, exposing the environment to unacceptable levels of risk. This approach fails to uphold professional standards of care and diligence. A third incorrect approach is to schedule a complete system shutdown for all virtual machines and then perform the host maintenance. While this guarantees no live migration issues, it introduces significant downtime, which is contrary to the goals of a high availability setup. This approach is inefficient and fails to utilize the advanced features of the virtualization platform designed to prevent such extensive outages. It demonstrates a lack of understanding of the benefits of virtualization for maintaining continuous operations. Professional reasoning. Professionals in this domain must adopt a proactive and risk-aware decision-making process. This involves thoroughly understanding the capabilities of the virtualization platform, the dependencies of the virtualized services, and the potential impact of any maintenance activity. A robust change management process, including detailed rollback plans, is essential. For high availability systems, the primary consideration should always be minimizing service disruption and data loss. This requires leveraging features like live migration, clustering, and automated failover mechanisms. Professionals should prioritize solutions that maintain service continuity and data integrity, adhering to established best practices and any relevant operational guidelines or regulatory mandates. Question 9. The performance metrics show a consistent increase in network latency and occasional packet loss between nodes in a critical high-availability Linux cluster. The cluster is running a virtualized environment, and the issue is impacting application response times. What is the most appropriate initial diagnostic step to pinpoint the source of this network degradation without causing service disruption? Option A. Initiate a live network traffic capture on the affected nodes using tools like TCP dump and analyze the captured data for anomalies, while simultaneously monitoring kernel-level network statistics and resource utilization. Option B. Immediately reboot all virtual machines and physical hosts within the cluster to clear any potential transient network states. Option C. Temporarily disable the firewall on all nodes to rule out any potential packet filtering issues. Option D. Systematically increase the MTU size on all network interfaces across the cluster to potentially improve packet throughput. The correct answer is A. Initiate a live network traffic capture on the affected nodes using tools like TCP dump and analyze the captured data for anomalies, while simultaneously monitoring kernel-level network statistics and resource utilization. Explanation. This scenario presents a common challenge in high-availability Linux environments, diagnosing performance degradation in a virtualized cluster without disrupting critical services. The professional challenge lies in accurately identifying the root cause of increased latency and packet loss, while adhering to strict operational uptime requirements and potentially sensitive data handling protocols inherent in enterprise Linux deployments. The need for a systematic, non-intrusive diagnostic approach is paramount. The correct approach represents best professional practice because it prioritizes data-driven, non-disruptive troubleshooting, utilizing specialized network analysis tools like TCP dump and Wireshark, combined with kernel-level performance monitoring, e.g., using perf or eBPF, allows for granular inspection of network traffic and system behavior without impacting the running services. This aligns with the principle of least privilege and minimizing operational risk, which are foundational in maintaining high availability and data integrity. Furthermore, such an approach facilitates accurate root cause analysis, leading to effective remediation and preventing recurrence, thereby upholding service-level agreements, SLAs, and client trust. An incorrect approach that involves immediately rebooting nodes or restarting network services without prior diagnosis is professionally unacceptable. This action constitutes a significant operational risk, as it can lead to unexpected service interruptions, data corruption, or even cascading failures in a clustered environment. Ethically, it violates the duty of care to maintain service continuity and could be seen as negligence if a less disruptive solution was available. From a regulatory perspective, depending on the industry, e.g., finance, healthcare, such an action could lead to non-compliance with uptime mandates and data availability requirements, potentially resulting in fines or reputational damage. Another incorrect approach, such as making broad configuration changes to network parameters, e.g., MTU buffer sizes across the cluster without isolating the problem, is equally problematic. This shotgun approach increases the likelihood of introducing new issues or exacerbating existing ones, making troubleshooting more complex. It demonstrates a lack of systematic problem solving and can lead to unintended consequences that are difficult to trace back to the original change. This reflects poor professional judgment and a failure to adhere to best practices in change management and incident response. The professional reasoning process for such situation should involve a structured incident response methodology. This typically includes 1. Incident identification and scoping, clearly defining the problem and its impact. 2. Data gathering, collecting relevant logs, performance metrics, and network traffic captures. 3. Hypothesis generation, forming educated guesses about potential causes. 4. Hypothesis testing, systematically verifying or refuting hypotheses using non-disruptive methods. 5. Root cause analysis, identifying the fundamental reason for the issue. 6. Remediation, implementing a solution. 7. Verification, confirming the issue is resolved. 8. Post-incident review, documenting lessons learned to prevent future occurrences. This systematic approach ensures that decisions are informed, risks are mitigated, and the most effective solutions are implemented. Question 10. The control framework reveals a critical failure in a primary virtual machine hosting a core financial application within a high-availability cluster. The system is configured with synchronous replication to a standby virtual machine. Given the immediate need to restore service and maintain data integrity, which of the following actions best adheres to established operational procedures and regulatory compliance for a senior Linux administrator? Option A. Restore the primary virtual machine from the most recent full backup, disregarding the status of the synchronous replication. Option B. Initiate a controlled failover to the synchronized standby virtual machine, ensuring all data changes up to the point of failure are replicated. Option C. Manually reconfigure a new standby virtual machine from scratch using the latest available system image. Option D. Immediately attempt to restart the failed primary virtual machine without further diagnostics, assuming a transient issue. The correct answer is B. Initiate a controlled failover to the synchronized standby virtual machine, ensuring all data changes up to the point of failure are replicated. Explanation. The scenario presents a common challenge in high-availability environments, balancing the need for rapid recovery with the imperative to maintain data integrity and adhere to established operational procedures. The professional challenge lies in selecting the most appropriate recovery strategy when faced with a critical system failure, ensuring minimal downtime without compromising the integrity of sensitive data or violating regulatory compliance. This requires a deep understanding of the underlying virtualization technology, the specific high-availability mechanisms in place, and the potential impact of different recovery actions on the overall system and its compliance posture. The correct approach represents best professional practice because it prioritizes a systematic, documented, and validated recovery process. This aligns with the principles of robust IT governance and risk management, which are often mandated by regulatory frameworks. By initiating a controlled failover to a pre-configured, synchronized replica, the system can resume operations with minimal data loss and within acceptable recovery time objectives, RTO. This method ensures that the failover process itself is tested and understood, reducing the likelihood of unforeseen issues during a critical event. Furthermore, it allows for proper logging and auditing of the recovery steps, which is crucial for compliance and post-incident analysis. An incorrect approach that involves immediately attempting to restart the failed node without proper diagnostics or a defined rollback plan introduces significant risks. This could lead to data corruption if the underlying cause of the failure is not addressed, potentially violating data integrity regulations. Another incorrect approach, such as manually reconfiguring a standby node from scratch, would likely exceed acceptable RTOs and could introduce human error, leading to misconfigurations that compromise availability and security. A third incorrect approach, like restoring from a recent backup without considering the synchronization status of replicas, could result in substantial data loss, failing to meet the high availability requirements and potentially violating service-level agreements, SLAs, and data retention policies. Each of these incorrect approaches demonstrates a failure to follow established disaster recovery and business continuity plans, which are often legally mandated or contractually required. Professionals should employ a decision-making framework that begins with understanding the nature and severity of the failure. This involves consulting monitoring tools and logs to diagnose the root cause. Next, they must assess the impact on critical services and data. The framework then dictates consulting the documented high availability and disaster recovery plans, which should outline predefined recovery procedures for various failure scenarios. The chosen recovery action must be evaluated against RTOs, recovery point objectives, RPO, and compliance requirements. Finally, the execution of the chosen recovery strategy should be meticulously logged and verified to ensure successful restoration of services and data integrity. Question 11. Market research demonstrates that organizations are increasingly adopting containerized applications for their agility and scalability. For a critical, stateful, containerized application running on a Linux cluster, which approach to implementing high availability would best align with senior-level best practices for virtualization and high availability, considering potential failover scenarios and resource management. Option A. Deploying a simple active-passive failover solution using a shared network file system and a basic heartbeat mechanism, as this is the most straightforward to configure. Option B. Relying solely on the container orchestration platform's built-in replication and load balancing features, assuming that the orchestration layer inherently provides sufficient high availability for stateful applications. Option C. Utilizing a proprietary clustering solution that offers extensive vendor support and a graphical user interface, prioritizing ease of management over deep technical understanding of the underlying clustering mechanisms. Option D. Implementing a distributed consensus-based cluster manager like Pacemaker with CoreSync, configured to manage the lifecycle of the containerized application and its persistent storage, ensuring automatic failover and resource arbitration. The correct answer is D. Implementing a distributed consensus-based cluster manager like Pacemaker with CoreSync, configured to manage the lifecycle of the containerized application and its persistent storage, ensuring automatic failover and resource arbitration. Explanation. This scenario presents a professional challenge in selecting the most appropriate high-availability clustering solution for a critical Linux-based application, balancing performance, cost, and adherence to established best practices within the LPI Level 3, Exam 300 for context. The core difficulty lies in evaluating the trade-offs between different clustering technologies and their suitability for specific application workloads and infrastructure constraints, all while ensuring compliance with the implicit regulatory framework of maintaining system integrity and availability, as expected in a senior-level certification. The correct approach represents best professional practice because it prioritizes a thorough, workload-driven evaluation of clustering technologies. This involves understanding the specific requirements of the application, such as its statefulness, communication patterns, and tolerance for failover latency. By considering factors like resource utilization, complexity of configuration, and community support, a senior Linux administrator can make an informed decision that maximizes reliability and minimizes potential downtime. This aligns with the professional responsibility to implement robust and maintainable solutions. An incorrect approach that focuses solely on the perceived ease of initial setup without considering long-term stability or scalability would be professionally unacceptable. This could lead to unexpected failures, performance degradation, and increased operational overhead, potentially violating the implicit requirement to provide a reliable and efficient service. Another incorrect approach that prioritizes proprietary solutions without a clear technical justification or cost-benefit analysis might overlook more efficient or open-source alternatives, leading to vendor lock-in and potentially higher long-term expenses, which is not a sound professional decision. Furthermore, an approach that ignores the need for robust monitoring and failover testing, even with a seemingly sound technology choice, demonstrates a critical oversight in ensuring actual high availability, failing to meet the core objective of the certification. The professional reasoning process should involve a systematic evaluation of available clustering technologies, e.g., pacemaker, chorusing, keep-lived, against the application's specific needs. This includes understanding the strengths and weaknesses of each in terms of failover mechanisms, resource management, and compatibility with the underlying Linux distribution. A critical step is to conduct proof-of-concept testing or pilot deployments to validate the chosen solution's performance and reliability under realistic load conditions. Finally, establishing comprehensive monitoring and regular testing procedures is paramount to ensuring ongoing high availability. Question 12. Compliance review shows that the organization's virtualized infrastructure, hosting critical financial data, must adhere to stringent data protection regulations requiring zero data loss and minimal downtime in the event of a catastrophic site failure. The current high availability solution is being re-evaluated to ensure it meets these evolving compliance demands. Which of the following approaches best aligns with these regulatory requirements for data integrity and availability? Option A. Deploy a shared storage solution with advanced RAID configurations within a single, highly resilient data center. Option B. Rely on frequent local backups of virtual machine data with a documented manual recovery procedure for disaster scenarios. Option C. Implement synchronous replication of virtual machine data to a geographically separate data center, coupled with automated failover mechanisms. Option D. Utilize asynchronous replication of virtual machine data to a remote site, prioritizing faster write performance at the primary location. The correct answer is C. Implement synchronous replication of virtual machine data to a geographically separate data center, coupled with automated failover mechanisms. Explanation: scenario analysis. This scenario presents a common challenge in enterprise virtualization environments where ensuring data integrity and availability is paramount, especially when dealing with sensitive data. The professional must navigate the complexities of distributed storage and replication mechanisms while adhering to strict data protection regulations. The challenge lies in selecting a high availability strategy that not only meets technical performance requirements, but also satisfies legal and compliance mandates regarding data residency, recovery point objectives, RPO, and recovery time objectives, RTO. Misinterpreting or misapplying these requirements can lead to significant legal penalties, reputational damage, and operational disruptions. Correct approach analysis. The correct approach involves implementing a synchronous replication strategy with geographically dispersed data centers. This method ensures that data is written to both primary and secondary locations simultaneously, guaranteeing that no data is lost in the event of a primary site failure. This directly addresses the RPO requirement of zero data loss, which is often a strict regulatory mandate for critical systems. Furthermore, synchronous replication, when coupled with robust failover mechanisms, can achieve very low RTOs, meeting compliance demands for rapid service restoration. The geographical dispersion also helps satisfy data residency requirements if applicable, ensuring data remains within a specified legal jurisdiction. This approach prioritizes data integrity and availability above all else, aligning with the core principles of data protection and business continuity mandated by regulatory frameworks. Incorrect approaches analysis. Implementing asynchronous replication, while offering better performance in some scenarios, fails to meet the zero RPO requirement. In the event of a primary site failure before data is replicated to the secondary site, data loss is inevitable, leading to a direct violation of data integrity regulations. This approach prioritizes performance over absolute data protection, which is unacceptable for compliance-driven environments. Relying solely on local backups without a robust disaster recovery plan and off-site replication exposes the organization to significant risk. While backups are crucial, they do not provide the continuous availability or immediate failover capabilities required by many regulations. Restoring from backups typically incurs substantial RTOs and does not guarantee zero data loss, making it insufficient for high availability and strict data protection mandates. Implementing a shared storage solution without geographical redundancy, even with RAID configurations, does not address site-level failures. A disaster affecting the primary data center would render the shared storage inaccessible, leading to complete service disruption and data unavailability. This approach lacks the necessary resilience for high availability and fails to meet regulatory requirements for business continuity and disaster recovery. Professional reasoning. Professionals must adopt a risk-based approach, prioritizing regulatory compliance and data integrity. The decision-making process should begin with a thorough understanding of all applicable regulations, including RPO, RTO, data residency, and data sovereignty requirements. This understanding should then be mapped against the capabilities of various high availability and disaster recovery technologies. A comparative analysis of these technologies, focusing on their ability to meet the defined compliance objectives, is essential. The chosen solution must demonstrably satisfy the most stringent regulatory demands, even if it involves a trade-off in other areas like cost or raw performance. Regular testing and validation of the implemented solution against disaster scenarios are also critical to ensure ongoing compliance and operational readiness. Question 13. System analysis indicates a critical virtual machine hosting a core business application requires scheduled maintenance on its underlying physical host. The organization operates under strict uptime requirements, and any significant service interruption is unacceptable. The virtualization environment is configured for high availability, considering the need to maintain continuous service operation and data integrity. Which method of relocating the virtual machine to a different host is the most professionally sound and compliant approach? Option A. Initiate a live migration of the virtual machine to an alternate host, ensuring the operating system and applications remain accessible throughout the transfer. Option B. Shut down the virtual machine, copy its disk image to a new host, and then start the virtual machine on the alternate host. Option C. Manually copy the virtual machine's disk files while the virtual machine is running and then attach them to a new virtual machine instance on the alternate host. Option D. Create a snapshot of the virtual machine, then power off the original virtual machine and restore the snapshot on the alternate host. Correct answer is A. Initiate a live migration of the virtual machine to an alternate host, ensuring the operating system and applications remain accessible throughout the transfer. Explanation. This scenario presents a common challenge in high availability environments, ensuring data integrity and service continuity during planned maintenance or unexpected failures. The professional challenge lies in selecting the most robust and compliant method for migrating virtual machines, VM, while minimizing downtime and adhering to the principles of virtualization and high availability as defined by the LPI Level 3 Exam 300 for syllabus. The core of the problem is balancing operational efficiency with the strict requirements for data protection and service uptime. The correct approach involves leveraging live migration capabilities inherent in modern virtualization platforms. This method allows for the seamless transfer of a running VM from one host to another with minimal or no perceived downtime for end users. This aligns directly with the high availability principles emphasized in the exam, as it directly addresses the need to maintain service continuity. From a regulatory and ethical standpoint, this approach minimizes disruption to business operations, which is often a key consideration in service-level agreements, SLAs, and compliance frameworks that mandate uptime. It demonstrates a professional understanding of how to manage critical infrastructure effectively and responsibly. Incorrect approaches fail to meet the standards of professional practice for high availability systems. Shutting down the VM and performing a cold migration, while technically feasible, introduces significant downtime. This directly contradicts the goal of high availability and could lead to breaches of SLAs, impacting business operations and potentially incurring penalties. Ethically, it represents a failure to employ the best available technology to maintain service continuity. Attempting to manually copy VM disk images while the VM is running is highly risky and prone to data corruption. This is a direct violation of data integrity principles and would be considered a severe professional failing, as it could lead to data loss and system instability, with significant regulatory and financial repercussions. Relying solely on snapshots without a clear migration strategy also fails to address the core requirement of moving the VM to a different host for maintenance or failover, leaving the system vulnerable. This approach does not actively manage the high availability aspect and could lead to extended downtime if a failure occurs. A professional reasoning process for such situations should involve a thorough assessment of the virtualization platform's capabilities, the specific requirements for downtime tolerance, and the potential impact on business operations. Professionals must prioritize solutions that align with high availability principles, minimize risk, and ensure data integrity. This involves understanding the nuances of live migration versus cold migration, the risks associated with manual data manipulation, and the importance of a well-defined disaster recovery and business continuity plan. Question 14. Risk assessment procedures indicate that a critical database cluster running on a high-availability Linux setup requires a robust data replication strategy to ensure minimal data loss and service interruption during planned maintenance or unexpected hardware failures. The primary concern is maintaining data consistency between the active and standby nodes. Considering the need for near-zero recovery point objectives, RPO, which of the following approaches best addresses this requirement for data replication? Option A. Implementing a synchronous or semi-synchronous block-level replication solution that ensures data is committed to both primary and secondary storage before acknowledging write operations. Option B. Utilizing a simple file-level copy command to synchronize the database directory from the primary to the secondary node. Option C. Configuring a synchronous replication where data is written to the primary and then replicated to the secondary with a slight delay. Option D. Relying on scheduled full and incremental backups to restore the database in case of a primary node failure. The correct answer is A. Implementing a synchronous or semi-synchronous block-level replication solution that ensures data is committed to both primary and secondary storage before acknowledging write operations. Explanation. Scenario analysis. This scenario presents a common challenge in high-availability Linux environments, ensuring data integrity and service continuity during planned maintenance or unexpected failures. The professional challenge lies in selecting the most appropriate method for data replication and synchronization that balances performance, reliability, and the specific requirements of the application and its data. The need for a robust, fault-tolerant solution that minimizes downtime and data loss is paramount, especially in a senior-level role where the impact of a poor decision can be significant. Correct approach analysis. The correct approach involves implementing a synchronous or semi-synchronous replication mechanism that guarantees data consistency across the primary and secondary storage. This ensures that any data written to the primary is immediately or near immediately committed to the secondary before the write operation is acknowledged to the application. This method directly addresses the requirement for zero or near-zero data loss during failover, which is a critical aspect of high availability. Such solutions, when properly configured and monitored, align with best practices for disaster recovery and business continuity planning, minimizing the potential for data corruption or loss, and thus adhering to implicit regulatory expectations for data integrity and service availability. Incorrect approaches analysis. Implementing asynchronous replication, while offering better performance for write operations, introduces a window of potential data loss. If a failure occurs on the primary before data is replicated to the secondary, that data will be lost. This is a significant regulatory and ethical failure in a high availability context where data integrity is paramount. Relying solely on periodic backups for failover is also insufficient for high availability. Backups are designed for disaster recovery, not for rapid failover with minimal downtime and data loss. The recovery time objective RTO and recovery point objective RPO for backups are typically much longer than what is acceptable for a high availability system, leading to unacceptable service disruption and data loss. Using a simple file-level copy without a robust synchronization mechanism is inherently prone to race conditions and data corruption, especially with active databases or frequently changing files. This approach lacks the transactional integrity required for high availability systems and would likely result in data inconsistencies and failures during a failover event. Professional reasoning. Professionals in this domain must adopt a risk-based decision-making process. This involves thoroughly understanding the application's data characteristics, its tolerance for downtime and data loss (RTO/RPO), and the underlying infrastructure capabilities. A comparative analysis of replication technologies, considering their synchronization modes, performance implications, and failure handling mechanisms, is essential. The chosen solution must be rigorously tested in a non-production environment to validate its effectiveness and reliability under various failure scenarios. Continuous monitoring and proactive maintenance are also critical components of a professional approach to ensuring high availability. Question 15. Operational review demonstrates that the current virtualized infrastructure supporting critical business applications is experiencing intermittent performance degradation during peak load times. The IT team is considering implementing a new high-availability clustering solution to improve resilience and potentially address performance bottlenecks. However, there is pressure to deploy a solution rapidly to mitigate ongoing user complaints. Which of the following approaches best represents professional best practice for implementing a new high-availability solution in this scenario? Option A. Postpone the implementation of any new high-availability solution until a comprehensive infrastructure overhaul can be completed, as introducing new components into a potentially unstable environment is too risky. Option B. Select a high-availability solution based on positive vendor testimonials and immediately deploy it to the production environment to address the performance issues and improve resilience. Option C. Conduct thorough testing of several candidate high-availability solutions in a dedicated staging environment that mirrors the production setup, including load testing and failover simulations, before selecting and deploying the most suitable option to production. Option D. Implement a basic high-availability configuration using readily available open-source tools, as this is the quickest way to achieve some level of resilience, and further optimizations can be addressed later. The correct answer is B. Select a high-availability solution based on positive vendor testimonials and immediately deploy it to the production environment to address the performance issues and improve resilience. Explanation. This scenario presents a professional challenge due to the critical nature of high availability in a production environment and the potential for data loss or service interruption. The need to balance performance optimization with the integrity and recoverability of virtualized systems requires careful consideration of established best practices and adherence to any relevant internal or external guidelines. The correct approach represents best professional practice because it prioritizes a systematic and controlled method for implementing changes. This involves thorough testing in a non-production environment to validate the effectiveness of the chosen high-availability solution and to identify any potential conflicts or performance degradation before impacting live services. This proactive stance minimizes risk and ensures compliance with the implicit requirement of maintaining service continuity, a cornerstone of responsible IT operations. An incorrect approach that involves directly applying a new high-availability solution to the production environment without prior testing is professionally unacceptable. This bypasses essential validation steps, significantly increasing the risk of unforeseen issues, service outages, and potential data corruption. Such an action could violate internal service level agreements, SLAs, and demonstrate a disregard for operational stability, leading to reputational damage and potential disciplinary action. Another incorrect approach, which involves implementing a solution based solely on anecdotal evidence or vendor marketing without independent verification, is also professionally unsound. This approach lacks the rigor required for critical infrastructure decisions and can lead to the adoption of solutions that are either ineffective, incompatible, or introduce new vulnerabilities. It fails to demonstrate due diligence and a commitment to evidence-based decision-making. A further incorrect approach, that of delaying the implementation of a high-availability solution due to perceived complexity or resource constraints without a clear mitigation plan, is problematic. While resource management is important, neglecting critical infrastructure improvements that directly impact service availability can lead to greater problems and costs in the long run when failures inevitably occur. This demonstrates a failure to proactively manage risk. The professional decision-making process for similar situations should involve a structured risk assessment, followed by the evaluation of potential solutions against defined criteria, e.g., reliability, performance, cost, compatibility. Pilot testing or proof-of-concept deployments in isolated environments are crucial before full-scale implementation. Documentation of the process, including testing results and rollback plans, is also essential for accountability and future reference. Question 16. Assessment of the most appropriate strategy for performing essential host maintenance on a critical virtualized application server within a high-availability cluster, where the primary objective is to maintain continuous service availability to end users with zero perceived downtime. Option A. Attempt to perform host maintenance while the virtual machine is actively running on the host without any migration or failover. Option B. Copy the virtual machine's disk image to another host and start it there after taking the original host offline. Option C. Initiate a live migration of the virtual machine to another available host node within the cluster before commencing host maintenance. Option D. Schedule a full shutdown of the virtual machine, perform host maintenance, and then restart the virtual machine. The correct answer is C. Initiate a live migration of the virtual machine to another available host node within the cluster before commencing host maintenance. Explanation. Scenario analysis. This scenario presents a common challenge in high-availability environments, ensuring data integrity and service continuity during a planned maintenance window for a critical virtualized service. Professional challenge lies in balancing the need for system updates with the imperative to minimize downtime and data loss, all while adhering to the specific operational guidelines and potential regulatory frameworks relevant to the LPI Level 3 Exam 300 for context, which implies a focus on robust, enterprise-grade Linux virtualization and high availability. The complexity arises from the interconnectedness of virtual machines, storage, and network components, where a seemingly minor misstep can cascade into significant service disruption. Correct approach analysis. The correct approach involves a meticulously planned and executed live migration of the virtual machine to a different host node within the cluster. This method leverages the underlying virtualization platform's capabilities to move a running VM, including its memory state, from one physical server to another without interrupting its operation. This is best professional practice because it directly addresses the requirement for zero or near zero downtime during maintenance. It demonstrates a deep understanding of high availability principles and the specific features of the virtualization software being used. This approach minimizes risk by avoiding a full shutdown and restart cycle, which inherently carries a higher probability of failure or extended downtime. From a regulatory or compliance perspective, within the implied scope of Enterprise Linux certification, this method aligns with best practices for business continuity and disaster recovery planning, ensuring that critical services remain accessible as much as possible. Incorrect approaches analysis. One incorrect approach is to schedule a full shutdown of the virtual machine, perform the host maintenance, and then restart the virtual machine. This is professionally unacceptable because it directly violates the implicit requirement for high availability. While it might be the simplest method, it introduces a significant downtime window, potentially impacting business operations and user access. Ethically and professionally, it fails to employ the available technologies to maintain service continuity. Another incorrect approach is to attempt to perform the host maintenance while the virtual machine is running on it, without any form of migration or failover. This is highly risky and unprofessional. It exposes the virtual machine to potential data corruption or unexpected crashes if the host hardware or software encounters issues during the maintenance. This approach disregards the principles of fault tolerance and high availability, and could lead to service outages and data loss, which would be a failure to meet operational standards and potentially regulatory requirements for data integrity and service uptime. A third incorrect approach is to simply copy the virtual machine's disk image to another host and start it there, assuming the original host is then taken offline. This is also incorrect because it does not account for the running state of the virtual machine's memory. This would result in a cold boot, effectively a restart, and would not be a live migration. It also doesn't address the potential for data inconsistencies that might have occurred between the disk image copy and the actual running state of the VM, leading to potential data loss or corruption. Professional reasoning. Professionals in virtualization and high availability must prioritize service continuity and data integrity. The decision-making process should always start with understanding the service's availability requirements. If high availability is a stated or implied requirement, then solutions that minimize or eliminate downtime are paramount. This involves a thorough understanding of the virtualization platform's features, such as live migration, clustering, and shared storage. Before undertaking any maintenance, a risk assessment should be performed, evaluating the potential impact of different approaches. The chosen method should be the one that best mitigates these risks while meeting the availability objectives. Documentation of the planned procedure, including rollback strategies, is also crucial. In situations where live migration is not feasible due to platform limitations or specific maintenance tasks, a planned, scheduled downtime with clear communication to stakeholders is the next best alternative, but it should not be the default choice when high availability is expected. Question 17. Comparative studies suggest that maintaining high availability in virtualized Linux environments during planned kernel and hypervisor updates requires a meticulous approach to minimize service disruption and data integrity risks. A senior system administrator is tasked with updating a critical high-availability cluster running multiple virtual machines, some of which host sensitive financial data. Administrator must choose a method that ensures continuous service availability and data protection throughout the update process. Which of the following approaches best aligns with best practices for maintaining high availability during such updates? Option A. Implement live migration of all virtual machines to other nodes in the cluster before performing kernel and hypervisor updates on individual nodes, followed by a phased restart of services. Option B. Schedule a maintenance window to shut down all nodes in the cluster, perform the updates on each node sequentially, and then bring the cluster back online. Option C. Manually initiate failover for critical virtual machines to standby nodes before applying updates to the active nodes, without pre-migrating all workloads. Option D. Perform individual node reboots for updates without migrating virtual machines, relying on the cluster's automatic failover mechanisms to bring services back online. The correct answer is B. Schedule a maintenance window to shut down all nodes in the cluster, perform the updates on each node sequentially, and then bring the cluster back online. Explanation. This scenario presents a common challenge in high availability environments, ensuring data integrity and service continuity during planned maintenance while adhering to strict operational procedures and potential regulatory compliance requirements. The professional challenge lies in balancing the immediate need for system updates with the imperative to minimize risk to critical services and sensitive data. Careful judgment is required to select a method that is both effective for the update and compliant with established best practices for virtualization and high availability. The correct approach represents best professional practice because it prioritizes a controlled, phased rollout that minimizes downtime and data loss risk. By leveraging the inherent capabilities of the virtualization platform for live migration and failover, it ensures that services remain accessible to users throughout the maintenance window. This method aligns with industry standards for robust high-availability solutions, emphasizing resilience and minimal disruption. Furthermore, it allows for thorough testing and validation at each stage, reducing the likelihood of unforeseen issues impacting production. An incorrect approach that involves shutting down the entire cluster for patching would be professionally unacceptable due to its direct violation of high-availability principles. This method introduces significant downtime, directly contradicting the purpose of a high-availability setup and potentially leading to service-level agreement (SLA) breaches. It also increases the risk of data corruption if the shutdown or subsequent restart is not handled perfectly. Another incorrect approach, performing individual node reboots without prior live migration, would lead to service interruptions for the virtual machines hosted on those nodes, again undermining the high-availability design and potentially causing data inconsistency for applications sensitive to abrupt terminations. A third incorrect approach, relying solely on manual failover without pre-migration and testing, introduces a higher degree of uncertainty and risk. While it might seem like a quicker solution, it bypasses crucial validation steps, increasing the chance of errors during the actual failover process and potentially leading to extended outages if issues arise. Professionals should adopt a decision-making framework that begins with understanding the specific requirements of the high-availability cluster, including the criticality of the services hosted, the acceptable downtime window, and any relevant compliance mandates. This should be followed by an assessment of the available tools and features within the virtualization platform that support live maintenance operations. A risk assessment for each potential maintenance strategy is crucial, weighing the likelihood and impact of failure against the benefits of the chosen method. Finally, a detailed rollback plan should always be in place to address any unexpected complications. Question 18. Quality control measures reveal that a critical component within the high-availability cluster's virtualization layer is scheduled for a mandatory security update. The update is known to introduce significant architectural changes. The current production environment consists of multiple active-passive nodes managed by a cluster manager, with live virtual machines running critical services. What is the most professional and risk-averse approach to applying this update? Option A. Apply the update to a single node in the production cluster while the cluster is running, monitor for immediate issues, and then proceed with other nodes if no problems are observed. Option B. Create a fully replicated staging environment that mirrors the production cluster's configuration and data. Apply the update to the staging environment. Thoroughly test all services and failover mechanisms, and then proceed with the update in production during a scheduled maintenance window after successful staging validation. Option C. Postpone the update indefinitely until a future major version release, as applying updates to a live high-availability system is inherently too risky. Option D. Apply the update directly to all nodes in the production cluster during a scheduled maintenance window, ensuring all virtual machines are gracefully shut down beforehand. The correct answer is D. Apply the update directly to all nodes in the production cluster during a scheduled maintenance window, ensuring all virtual machines are gracefully shut down beforehand. Explanation: this scenario presents a common challenge in high-availability environments, ensuring data integrity and service continuity during planned maintenance. The professional challenge lies in balancing the need for system updates with the imperative to minimize downtime and data loss, all while adhering to strict operational procedures and potentially regulatory compliance requirements for data handling and system availability. The chosen approach must demonstrate a thorough understanding of virtualization technologies, high availability concepts, and robust change management practices. The correct approach represents best professional practice because it prioritizes a phased, controlled, and validated rollout of the update. This method minimizes risk by allowing for early detection of issues in a non-production environment before impacting live services. It also ensures that rollback procedures are tested and readily available, a critical component of any high-availability strategy. This systematic approach aligns with principles of operational excellence and risk management, which are often implicitly or explicitly required by IT governance frameworks and best practices, ensuring that changes are implemented in a predictable and recoverable manner. An incorrect approach that involves directly applying the update to the production cluster without prior testing in a staging environment is professionally unacceptable. This bypasses crucial validation steps, significantly increasing the risk of introducing bugs or incompatibilities that could lead to widespread service disruption, data corruption, or complete system failure. Such an action demonstrates a disregard for established change management protocols and a failure to adequately assess and mitigate risks, potentially violating service-level agreements, SLAs, and leading to reputational damage and financial penalties. Another incorrect approach, applying the update to a single node in the production cluster and hoping for the best, is also professionally unsound. While it might seem like a limited test, it fails to account for cluster-wide interactions, potential quorum issues, or cascading failures that could arise from an update that affects the entire cluster's functionality. This approach lacks the rigor of a dedicated staging environment and does not provide sufficient confidence in the update's overall stability and compatibility within the complex high-availability architecture. A third incorrect approach, delaying the update indefinitely due to fear of disruption, is also professionally detrimental. While caution is warranted, complete avoidance of necessary updates can lead to security vulnerabilities, performance degradation, and an inability to leverage new features or bug fixes. This passive stance can ultimately increase risk over time as systems become outdated and unsupported, potentially violating compliance mandates that require systems to be maintained at a certain patch level. Professional reasoning process for such situations involves a structured risk assessment. This includes identifying potential impacts of the change, evaluating the likelihood of adverse events, and determining appropriate mitigation strategies. A key element is the establishment and utilization of a robust testing and staging environment that mirrors the production setup as closely as possible. This allows for thorough validation of the update, including functional testing, performance testing, and failure scenario testing. Furthermore, a well-defined change management process, including rollback plans and communication strategies, is essential for successful and safe implementation of any system modification in a high-availability context. Question 19. To address the challenge of ensuring continuous operation and data integrity, For a critical virtualized application cluster, a senior Linux administrator must implement a storage solution that can withstand individual node failures without service interruption. The existing infrastructure utilizes multiple physical servers for the application and requires a shared, highly available storage backend. The administrator is evaluating different storage architectures to meet these stringent uptime requirements. Which of the following storage architectures is most appropriate for achieving high availability and fault tolerance in this virtualized environment? Option A. A manual snapshotting and replication process of the application's data to a separate, offline storage medium. Option B. A distributed file system employing replication or erasure coding across multiple storage nodes. Option C. A network file system (NFS) or server message block (SMB) share hosted on a single dedicated file server with no redundant storage. Option D. A single, high-capacity direct attached storage DAS device connected to one of the application servers. The correct answer is B. A distributed file system employing replication or erasure coding across multiple storage nodes. Explanation. This scenario presents a professional challenge due to the critical nature of high availability in a production environment and the potential for data loss or service interruption. The requirement to implement a robust, fault-tolerant storage solution necessitates a deep understanding of distributed file systems and their failure modes. Careful judgment is required to select a solution that not only meets performance and availability targets, but also adheres to best practices for data integrity and recovery. The correct approach represents best professional practice because it leverages a distributed file system specifically designed for high availability and fault tolerance, such as Ceph. Ceph's architecture, with its use of replication and erasure coding, ensures data redundancy across multiple nodes. This design inherently mitigates the risk of data loss due to single points of failure, a core tenet of high availability. Furthermore, Ceph's ability to dynamically rebalance data and recover from node failures without manual intervention aligns with the principles of automated fault tolerance, minimizing downtime and operational overhead. This aligns with the general principles of ensuring system resilience and business continuity, which are implicitly expected in senior-level certifications focused on virtualization and high availability. An incorrect approach that involves a single, non-replicated storage device fails to meet the fundamental requirements of high availability. This creates a single point of failure, meaning any hardware malfunction or network issue affecting that device will lead to complete service disruption and potential data loss. This is a direct violation of the principles of fault tolerance and resilience expected in a high availability context. Another incorrect approach that relies on manual snapshotting and replication to a secondary location, while a form of backup, is not a true high availability solution. Manual processes are prone to human error, delays in execution, and are reactive rather than proactive in preventing downtime. If a failure occurs between manual snapshots, data loss is inevitable. This approach does not provide the continuous availability or automatic failover that defines a high availability system. Third incorrect approach that uses a network file system, NFS, or server message block, SMB share without a robust underlying high availability storage backend is also insufficient. While these protocols facilitate shared access, their inherent availability is dependent on the reliability of the server hosting the share. If that server or its storage fails, the shared data becomes inaccessible, negating any high availability claims for the services relying on it. The professional reasoning process for similar situations should involve a thorough assessment of the availability requirements, potential failure scenarios, and the capabilities of different technologies. This includes understanding the trade-offs between cost, complexity, and resilience. A structured approach would involve 1. Defining clear RTO recovery time objective and RPO recovery point objective for the services. 2. Identifying critical components and potential single points of failure. 3. Evaluating storage solutions based on their fault tolerance mechanisms, replication, erasure coding, clustering. 4. Considering the operational overhead and management complexity of each solution. 5. Prioritizing solutions that offer automated failover and recovery capabilities. 6. Documenting the chosen solution and its rationale, including any assumptions made. Question 20. Compliance review shows that a critical virtualized cluster supporting financial transaction processing is scheduled for a kernel update. The current setup utilizes active-passive high availability. The update requires a reboot of the underlying host operating system. What is the most compliant and professionally sound approach to perform this kernel update while minimizing risk to data integrity and service availability? Option A. Perform the kernel update and reboot on the primary node while services are still running, assuming the update process is non-disruptive. Option B. Initiate a planned failover of all services to the passive node, perform the kernel update and reboot on the primary node, then fail back services once the primary is confirmed to be operational. Option C. Restore the cluster from a full backup taken at the beginning of the business day. Perform the kernel update and reboot on the primary node, then bring services back online. Option D. Schedule a brief maintenance window where all services are stopped. Perform the kernel update and reboot on the primary node, then restart services. The correct answer is B. Initiate a planned failover of all services to the passive node, perform the kernel update and reboot on the primary node, then fail back services once the primary is confirmed to be operational. Explanation. The scenario presents a common challenge in high availability environments, ensuring data integrity and service continuity during planned maintenance, while adhering to strict regulatory requirements for data protection and auditability. The professional challenge lies in balancing the need for system updates with the imperative to maintain uninterrupted service and prevent data loss or corruption, all within the confines of the exam-specified regulatory framework. This requires a deep understanding of virtualization technologies, clustering mechanisms, and the specific compliance mandates governing such operations. The correct approach represents best professional practice because it prioritizes a phased, controlled migration of services to a secondary node. This method minimizes downtime by allowing services to continue running on the primary node until the secondary is fully ready to take over. It also ensures data consistency through synchronous replication or a robust, verified backup and restore process immediately preceding the cutover. This aligns with regulatory principles that demand data integrity, availability, and the ability to demonstrate a controlled, auditable process for system changes. The emphasis on pre-migration testing and post-migration validation further reinforces compliance by providing evidence of due diligence and successful execution, crucial for audit trails. An incorrect approach that involves shutting down the entire cluster for maintenance, even for a short period, fails to meet high availability requirements and potentially violates service-level agreements, SLAs, and regulatory mandates for continuous operation where applicable. This lack of redundancy during the maintenance window exposes the system to unacceptable risk. Another incorrect approach, performing the update on the primary node without a prior, verified failover to a secondary, directly risks data loss or corruption if the update fails. This bypasses critical safety checks and fails to demonstrate a commitment to data integrity and service resilience, which are often core tenets of regulatory compliance. It also creates an unacceptably long downtime if issues arise during the update. A third incorrect approach, relying solely on a backup taken days before the maintenance, is insufficient. This fails to account for data changes that may have occurred between the backup and the maintenance window, leading to potential data loss. Regulatory frameworks typically require data to be current and consistent, and a backup that is not immediately prior to a critical operation does not guarantee this. The professional reasoning process for such situations involves a thorough risk assessment, understanding the specific high availability architecture, and meticulously planning the maintenance window. This includes identifying critical services, understanding their dependencies, and defining rollback procedures. The decision-making framework should always prioritize data integrity, service continuity, and adherence to all applicable regulatory requirements, ensuring that any maintenance activity is performed in a manner that is both safe and auditable.